All right, in section 5.1, this is all about, for Math 1613, this is all about just angles. We have our objectives here. I'll let you read those. All right, the big thing that we're going to be covering that I think is the most important is these conversions, these coterminals, and drawing your angles. An angle is the union of two rays that have a common endpoint. So a ray has a beginning and a direction. So if you have a union of two rays, that means they have the same endpoint, like this angle here. And the way we label this angle is the vertex, which is that corner, that common endpoint, is in the middle. So we have the point on the side, and then we have the vertex, and we have a point on the other side. And it doesn't matter the order. I could say F, E, D as well, but the E would always be in the middle. Okay, an angle that is in standard position. Okay, standard position. So if its vertex is located at the origin, so that corner is now at the origin of a coordinate plane. Okay, and then the initial side, okay, this is the beginning. It's on the positive x-axis. Okay, so we have initial side, vertex, and the rotation of your angle is shown by the terminal side. All right, so in standard position, vertex is at the origin, initial side on the positive x-axis, with rotation showed by the terminal side. Okay, positive angles rotate counterclockwise. If an angle has been rotated clockwise, so direction is different, then it is a negative angle. So I still have my vertex at the origin. Initial side is still the positive x-axis, but now I'm rotating clockwise, which would mean that this angle is negative. There are several different variables that we use to represent an angle. A lot of the times we use Greek letters to represent the measure of an angle, and our main one is theta. Okay, and some of our trigonometric identities later on, you're going to see alpha and you're going to see beta. Okay, these other ones show up every now and then, but the one that shows up the most often is your theta. All right, I'm not super great at drawing those. Those can be, sometimes they look really neat, sometimes not so much. It's okay. The measure of an angle, it simply means the amount of rotation, okay, from the initial side to the terminal side. 360 degrees in a full rotation of a ray. So that means 1 degree is 360, so 1 out of 360 of a full rotation. All right, an angle is quadrantal. We use that one a lot. Angle is quadrantal if its terminal side falls on an axis, whether that's the x-axis or the y-axis. So for example, 0 degrees, no rotation whatsoever, is quadrantal because its terminal and its initial fall on the x-axis. And we've got 9 degrees. All right, 90 degrees is 1/4 of a rotation, 1/4 of a rotation. Initial side, terminal side, that's the positive y-axis. 180 degrees, initial side, terminal side, that's the negative x-axis. We've got 270 degrees, initial side, terminal side, rotating around 270 degrees. And of course, 360 would be the full rotation around. Okay, now the order of your quadrants. Okay, quadrant 1 goes counterclockwise, 2, 3, 4. And this is one of the big ones I was telling you about, converting between degrees and radians. What is a radian? Okay, a radian, to kind of keep it short, is an angle measure that's based off of arc length instead of rotation. So a radian, highlight, is the measure of a central angle of a circle that intercepts an arc that is equal in length to the radius of a circle. Okay, well, going back to previous math courses, a central angle is an angle formed at the center of the circle by 2 radii. So vertex is on the origin, and 2 radius makes the angle. Total circumference of a circle equals 2 pi times the radius. That means a full rotation. One full rotation is 2 pi radians. All right, so you can see some equivalencies here. One full rotation, 360 degrees, 2 pi radians. Half a rotation, half of 360 is 180. Half of 2 pi is pi. 1/4 of a rotation, okay, and that's half of a half. So half of 180 is 90. Half of pi over 2. Okay. So how this relates to arc length S is the curve along the arc of a circle. Think of it like the perimeter of a circle. All right, we have a formula for arc length. Arc length is radius times theta. Okay, arc length, radius times theta. So solving for theta, your angle, I would divide both sides by r. So we take and divide both sides by r. So I can see that theta equals s over r. Okay, well, a radian is specific to arc length equals the radius. So arc length equals the radius, which means theta really equals radius over radius, which is 1. So how many radians does it take to get all the way around the circle? Well, that's 1 full rotation. That's 2 pi radians. All right, find the radian measure of 1/3 of a full rotation. We've got 1/3 of a full rotation. A full rotation is 2 pi. 1/3 of that would be 2 pi divided by 3. That's your radian measure. 1/3 of a full rotation is 2 pi over 3. Now in degrees, 1 full rotation, 360 degrees, divided by 3. That's 120, and I can see that. There's initial side, terminal side. And I can see the full rotation right there. Find the radian measure of 3/4 of a rotation. Okay, so a rotation again is 2 pi. Okay, 3/4 of it. Okay, I'm gonna multiply this by 3/4. All right, well, using our algebra here, our math, 2 goes into 4 twice. Multiply across the top. 5 times 3 is 3 pi. 1 times 2 is 2. 3 pi over 2. Okay, if we do that for degrees, 360 degrees times 3/4. Remember, we put that over 1. All right, so 4 goes into 360 90 times. 90 times 3 is 270 degrees. So that puts me down here. All right, so because degrees and radians both measure angles, you need to be able to convert back and forth between the two of them. Okay, there is a conversion factor. Okay, if I want to go from degrees to radians, so degrees to radians, we multiply by pi over 180. Okay, so degrees to radians. Multiply your angle by pi over 180 degrees. Radians back to degrees, multiply by 180 over pi. It's reciprocal. convert each radian measure to a degree measure. So I'm converting radians to degrees, which means I must be multiplying by 180 over pi. All right, so in this case, pi cancels pi. Okay, reduces to 1. All right, so I have 180 over 6. Well, I also know that 6 goes into 180 30 times. So pi over 6 in degrees is 30 degrees. I don't know, it's an incredibly common misconception that all radians have a pi. Okay, how you can tell a radian from a degree is literally just the symbol. Right, this 3 is missing the degree symbol. Therefore, it's radians. Okay, no degree symbol, it's radians. So to convert it to degrees, I'm going to multiply by 180 degrees over pi. Okay, it's not going to be pretty, but it is what it is. So now I got to think 36, me without my calculator. It's 54, so 540 degrees over pi. Negative 3/4 or 3 pi over 4. It does not matter that it's negative. That just means we rotated clockwise instead of counterclockwise. So switching to degrees, that's 180 degrees over pi. Okay, in this case, pi is going to cancel pi. Okay, 4 goes into 180. Okay, no goes in twice, so 2. So that's 90, and then 2 goes into 90 45 times. Let's see. It's 135 degrees negative. Converting each degree back into radian, that's multiplication by pi over 180 degrees. So the degree symbol cancels. I know this reduces 3. So that's 5. That's 60, and then 5 goes into 60 12 times. So I get pi over 12. Now you can do this in the calculator. So let me show you how to do it. You just can't use the pi symbol. And so what we do instead of using a pi is we just use 1. I just have to remember that's where the pi goes. So if I want to change 15 to radians, I'm going to use Desmo Scientific here. I would do 15 times 1 over 180, and then change that to its fraction, which is 1/12, and then multiply by pi. All right, so B, changing from degrees to radians, that's multiplication by pi over 180 degrees. Degrees cancel. Let's see, I know 2 goes in. 63 times 90. Forgot to change my color. 3 goes in. 21 and 30. 3 again. 7, 10. This would be 7 pi over 10. I probably should have just used my calculator. I don't feel like getting it out, but I'm going to show you now. So 126. Remember, don't use your pi because it's going to change it to a decimal. So I'm going to do 126 times 1 over 180. Change to its fraction, so 7/10. I was right. negative 75 degrees. Okay, doesn't matter that it's negative, it's just rotating clockwise instead of counterclockwise. Multiply by pi over 180. Degrees cancel. This one I'm not super sure, so I'm going to go ahead and do this one in the calculator. So I'm going to do negative 75 times 1 over 180. So negative 5 over 12. Multiply by pi, so negative 5 pi over 12. All right, now we're going to be converting decimal degrees to degrees, minutes, seconds. And where you see degrees, minutes, seconds, this is usually used a lot in navigation with like latitude and longitude. So it's a more like precise way directionally of figuring out where something is. Okay. So a decimal degree can be measured in degrees, minutes, seconds. 1 minute, if we think logically on this, 1 minute is 1/60th of, just lost my train of thought. So how many minutes are in a circle? 60. A second is 1/60th of that. All right. So to convert, okay, from, this is considered decimal degrees. And we're converting to degrees, minutes, seconds. All right, so we start by taking the whole number. Let's make that smaller. We're going to keep that off to the side. That's our whole, 42 degrees. And you're going to take this 0.125, the remaining decimal, and you're going to multiply it by 60. .125 times 60. That's 7.5. Okay, we're going to take that whole number again. This time it's the 7. And that is our minutes. We're going to take the decimal that's left one more time. And we're going to multiply by 60 one more time. That's going to get our seconds. So 0.5 times 60, that's half of 60, which is 30. So 42.125 degrees in degrees, minutes, seconds. 42 degrees, 7 minutes, 30 seconds. Okay, now to convert back, going from degrees, minutes, seconds, we've got 117 degrees, 15 minutes, 45 seconds, and I want to convert them back to decimals. So this is DMS, back to decimal degrees. Okay, we're going to start with the whole number. Okay, and we're going to add. Okay, next one is minutes. Well, how many minutes are in an hour? Okay, 60. So this would be 15 out of those 60. That's your minutes. Then that 45, how many seconds are in an hour? That's 3,600. All right, now I'm 100% not going to make you do this by hand. We're going to do this in the calculator. So 117 plus 15 over 60 plus, I already forgot what it was, 45 over 3,600. All right, we can see it over here on the side, 117.2625. Moving right along, now we're getting into something called a coterminal angle. So I want you to remember that an angle in standard position has an initial side on the positive x-axis and a terminal side that shows the rotation. Okay, so if all I have is this, If you can see my lasers over here. Without any rotation, this could mean a whole bunch of different things. It could mean that 38 degrees. Great. But what if I rotated the other direction? Okay, now it represents the negative 322. What if I rotate more than once? Okay, the initial drawing is still the same. Initial side, terminal side, but the angle measure is different. So if the picture is the same, okay, the terminal and the initial side are the same, but your angle measures are different, they're considered coterminal angles. Okay, you can rotate around, this is what people forget, is that you can rotate around the circle clockwise or counterclockwise infinitely many times. What this means for us is that you have infinitely many coterminal angles, because you can either add or subtract 360 or 2 pi, resulting in an angle that has the same terminal initial side. Find an angle theta that is coterminal with an angle measuring 870 degrees, where theta is between 0 degrees and 360 degrees. So it needs to be between 0 and 360 degrees. Well, 870 is obviously too big. So I'm going to take 870 and I'm going to subtract 360. Try and do that in my head. It looks like it's going to be 510 degrees. Okay, that's not between 0 and 360, so we do it again. All right, now I'm going to have to use my old subtraction algorithm. So that's 150 degrees. Okay, 150 degrees is between 0 and 360. Find an angle beta that is coterminal with an angle measuring negative 300 degrees. So negative 300 degrees being rotated clockwise, probably somewhere in here. Okay, so I'm going to add 360. And that gives me my positive coterminal angle that's between 0 and 360 degrees. Find an angle beta that is coterminal with 19 pi over 4, where beta is between 0 and 2 pi. So the first thing I want to do is figure out what 2 pi is when it's over 4. So I'm going to put 2 pi over 1, change my denominator to 4. Okay, so if I had to multiply the 1 by 4, I have to multiply the 2 pi by 4, so it's going to be 8. Should always be double the denominator, because 2. So I'm going to take 19 pi over 4, subtract 2 pi, which is 8 pi over 4. So that's going to give me 11 pi over 4. Okay, well, I already know 2 pi should be 8 pi over 4, so this is still too big. I'm going to do this one more time. Now I have 3 pi over 4. Okay, well, 3 pi over 4 is greater than 0, but it is less than 8 pi over 4. So I've got my coterminal angle that it's asking for. 11 pi over 4 is a coterminal angle. It just doesn't meet these qualifications. It's not between 0 and 2 pi. So that's the big thing with your coterminals, is that make sure you're reading the directions. Okay, find an angle measure theta that is coterminal with the angle measure negative 17 pi over 6, where theta is between 0 and 2 pi. So just like I did over here, I'm going to figure out what 2 pi is when it's over 6. All right, so to multiply by 6, so it's going to be 12 pi over 6. Okay, so my angle has to be between 0 and 12 pi over 6. So let's take negative 17 pi over 6 and add 12 pi over 6. So that's going to be negative 5 pi over 6. That is a coterminal angle. I added a full rotation. it just doesn't meet these guidelines. It has to be between 0 and 2 pi. This is negative. Let's try it again. Seven pi over 6. That is also coterminal. Okay, it is greater than 0 because it's positive, but it is less than 12 pi over 6. So it meets our guidelines. This is the angle it's looking for. All right, let's revisit arc length. In a circle with radius r, the length with an arc subtended just means spanned. With angle measure in highlights, please. Theta is in radians. Is arc length equals radius times theta, where theta is in radians. Okay, again, it's literally measuring a piece of the circumference. All right, so find the arc length along a circle of radius 10 inches subtended by an angle of 215 degrees. I have radius. Radius is 10 inches. However, my angle, 215, is in degrees. So I need to take 215 and change it to radians. Multiply by pi over 180 degrees. So degrees cancels. I'm going to put that in my calculator. Oh, 43 over 36. Okay, so arc length equals radius times theta. Okay, so that's going to give me 430 pi over 36. I'm going to go ahead and put that in the calculator. 430 over 36. I'm just trying to get the fraction there, 215 over 18. All right, now, still on this example with our angle 215 degrees, they happen to want the decimal, say rounded to the nearest 10th, 100th, or 1000th, or whatever. 215 over 18. Okay, I'm going to change that back to its decimal. And then hit answer, and then I want to take that and I'm going to multiply it by pi. So it's 37.525. Okay, just make sure you're following the directions. Right, assume the orbit of Mercury around the sun is a perfect circle. Mercury is approximately 36 million miles from the sun. In one Earth day, the Mercury completes 0.0114 of its total revolution. Okay, so one Earth day, Mercury completes this decimal of a total revolution. Determine the radian measure for Mercury's movement in one Earth day. So for Mercury, so let's say radians. So it completes 0.10114 of the total revolution. So that's times 2 pi. That goes in your calculator, which I've already done. So 0.072. How many miles does Mercury travel in one day? It's asking for arc length. Arc length is radius times theta when theta is in radians. I have the theta, that's 0.072. Radius, that comes from the question itself. Assume the orbit of Mercury around the sun is a perfect circle. Mercury is approximately 36 miles from the sun. So if we imagine the sun, and here's Mercury, this distance, 36 million miles, it's rotating around. That's probably the wrong direction, but it's fine. So arc length, radius, 36 million miles. I'm just going to do 36 million. I don't feel like writing that many zeros. Times theta. Okay, so I'm going to do 36 times 0.072. To 2.592. Million miles. All right. You can also use angles to find the area of a sector. So an area of a sector is a piece of the area of a circle. It's a piece of pie, basically. All right, so we see that formula, area of a sector. Okay, that's the rotation, it's the angle out of 2 pi, times the formula for area of a circle. Okay, so this represents your fraction of the area. Simplifying that gives us 1/2 theta times radius squared. Okay, where theta is in radians. So theta is in radians. Okay, in a central pivot irrigation, a large irrigation pipe on wheels rotates around a center point. Farmer has a central pivot system with radius 400 meters. So we have radius. It's always a good habit to just write down what you know, because you may need it. If water restrictions will only allow her to cover 150,000 square meters, okay, so that's square meters right here. That tells me that this 150,000 is an area. What angle should she set the system to cover? All right, so area of a sector equals 1/2 theta times radius squared. So there are 3 variables there. Area, theta, radius. I have radius and I have area, which means I have enough to solve for theta. Okay, so area, nope, pen. So 150,000, 1/2 theta times radius squared. I'm going to do this without a calculator for the most part. Okay, so the first thing I'm going to do is get rid of the 1/2, and I'm going to do that by multiplying both sides by 2. Multiply by the reciprocal of 1/2. So that's going to give me 300,000. I am also going to go ahead and evaluate 400 squared. 400 squared is 160,000. And again, you can always do that in the calculator. 400 squared. Okay, so we're going to divide both sides by 160,000. Again, you can do this in your calculator if you want to, which is what I'm going to do. No, we're not graphing. We're going here. 300,000 divided by 160,000. 15/8. So theta equals 15 over 8. All right, last little bit, linear and angular speed describing motion. So linear speed, velocity, is speed along a straight path and can be determined by distance it moves along, so the placement in a given time interval. And the resulting speed will be the length in the time unit. So this is like miles per hour. So velocity equals s over t. This is change in position over change in time. All right, angular speed, this little w is an omega. Results from circular motion can be determined by the angle through which the point rotates in a given time interval. Okay, so the resulting speed will be in radians per time unit. Okay, and that's the formula right here. Omega equals theta in radians over time. So if we combine those two definitions, okay, with arc length equals radius times theta, okay, we can solve the angular speed, so this guy, for theta, which give me theta equals omega times time. If we sub this back into our arc length, we get arc length equals radius times theta. Well, theta is omega times time. So it's kind of a translation between the two. If we kind of manipulate all those around, okay, this is knowing that arc length is radius times omega times time. Velocity is change in position, so arc length over time. So arc length is radius times omega times time. This is over t. T's cancel. Velocity equals radius times omega. Theta must be in radians. Okay, that's a lot. The pieces that you need to know are linear. Velocity equals change in position over change in time. Okay, so this is arc length. I say change in position, but we need to use the right vocabulary here. This is arc length. Angular speed. Omega equals theta over time, theta in radians. And then the relationship between the two is that velocity equals radius times omega. An old vinyl record played on a turntable rotating clockwise. 45 rotations per minute. Find the angular speed in radians per second. Angular speed, omega equals theta over time. I need a theta, and I need a time. All right, well, theta I can find here, 45 rotations per minute, specifically the 45. Okay, well, theta is a rotation, right? So I have 45 of them. Okay, one rotation is 2 pi. So the total angle will be 90 pi radians. Okay, in that 45 rotations per minute, I also see the time is minute. So time, okay, 1 minute, but I need it in seconds, so that's 60 seconds. All right, so omega, angular speed, theta over time, 90 pi over 60 seconds. So this is radians, seconds. Let's see, zeros cancel, divided by 3. So I have omega as 3 pi over 2 radians per second. And you can do this in your calculator too. So I'm going to do 3 over 2 times pi. It's 4.712. Radians per second. A satellite was rotating around Earth at 0.25 radians per hour at an altitude of 242 kilometers above Earth. If the radius of the Earth is 6,378 kilometers, find the linear speed. So I have this angle measure here. Okay, well, how can I relate linear speed to this angle? Well, that's velocity equals radius times omega. Okay, which means I need a radius. I also need an omega. Okay, let's talk about the radius. All right, so if I have Earth and I have a satellite, okay, above Earth, 242 kilometers. Okay, but the radius of the Earth itself is 6,378 kilometers. So the total radius all of this, we're going to add those two together. Okay, so 6,378 plus 242 is 6,620 kilometers. Okay, now I need omega. Okay, omega is in radians per time unit. We have that. Radians per time unit. 0.25 radians per hour. So I've got all the parts here. Okay? So velocity equals radius, 6,620, times omega. All right, so we're going to do 6,620 times 0.25, 1,655. And that is in kilometers per hour.